Now, the differences between an E field and a B field. So, we just said that a moving charge produces a magnetic field. So, if I had a moving charge placed within a magnetic field, the moving charge itself is producing a magnetic field which is going to interact with the field that it is placed in. Because of this interaction, there would be a force applied on the moving charge. This is very well explained in the second diagram on page 14, where the moving charge is replaced with a current carrying conductor, which is basically a line of moving charges. So when these charges move, as we saw, the current carrying conductor produces its own magnetic field, and this would interact with the magnetic field that it is placed in, and therefore there would be a force on this conductor. Now, if there in an electric field you have a force on all charges, okay, whether they are stationary or moving. But in a magnetic field, you have a force on charges only under two conditions. Firstly, they should be moving, and not just moving in any direction, but in a direction perpendicular to the magnetic field. Okay? So, for example, if I have magnetic field lines like this, and I placed a current carrying conductor in this direction, okay, and let's say the length of this conductor is L, okay, the angle that this conductor makes with the conductor that makes with the normal here is theta. Okay, so in this case, okay, let's say the conductor is making an angle theta with the horizontal over here, like this. Okay, so what I want to do, this conductor has a current flowing in it with a strength I. So I current, B is the magnetic field, L is the length of the conductor, and it's placed at an angle theta. Now, I know that the moving charges in this conductor are going to experience a force, but only the component perpendicular to the magnetic field will experience a force. So, the force is going to be stronger if 1, the magnetic field is stronger, 2, if the current flowing is stronger, and 3, if the conductor itself is longer. So if it's a long conductor, it will experience a stronger force. So you have the force given by the multiplication of magnetic field, current, and the length of this conductor, and also we are only considering the perpendicular component of this conductor. So we will have to multiply with a factor of sine theta, where theta over here in this case is the angle made by the horizontal. Okay, so this in an exam situation you can have a sine theta term or a cos theta term depending on where this angle is, whether it's the angle from the horizontal or whether it's the angle from the normal. So you will have to ask the students to be careful and check that in every scenario, that you're only considering the perpendicular component of the conductor with the magnetic field. So you should not they should not rely on this term sine theta. So okay, and in order to determine the direction of this force, instead of seeing the interaction of magnetic fields, they can simply use the Fleming's left-hand rule. The Fleming's left-hand rule is basically using the first 3 fingers. The thumb represents force, the forefinger represents the magnetic field, and the middle finger represents the direction of current, FBI. So in this case, for example, you have the current moving upwards, since we are only considering the perpendicular component. Okay, the B field is towards the right, so you can see that the force is actually into the plane of the page. And how do you represent that? Across within a circle would be the representation of the force moving into the plane of the page. Why? Because this looks like the back end of an arrow, and the front end of an arrow would look like this, which represents coming out of the plane of the page. So in this case, you have the force moving into the plane of the paper. Okay, so again, we talked about a current carrying conductor of length L. Now, if you were to be talking about moving charges, individual charges, so let's say a charge is moving in a magnetic field with a velocity v. Okay, so with a velocity v, for example, in relation to this conductor, it would be covering L. The velocity would be given by the distance covered divided by the time taken. Okay, and the charge itself, let's say the charge itself is q. You can represent q as I multiplied with t. Okay, so if I had to substitute I equals q over t and the velocity equals the distance covered over the time taken into this equation, I have the force on the charge given by B multiplied with q over t multiplied with so L over here can be replaced with Vt. T and t get cancelled, and we also have a sine theta term over here. So therefore, force would be BQV sine theta. Okay, so this is the force, magnetic force, on a moving charge of charge q with a velocity v in a magnetic field of B. And theta in this case again is the angle that the charge makes with the magnetic field lines. Okay, over here theta was the angle made by the conductor with the magnetic field lines, and in this case it's the angle that the charge is making with the magnetic field lines. Okay, so let's look at this in a little more detail. So you have F equals BQV sine theta. Let's say a charge, a positive charge, enters a magnetic field with a velocity v. Okay, so the magnetic field is pointing into the plane of the page. This charge is moving with the velocity v in it, and it has a charge of q. So the force, there will be a force applied on this charge of strength F equals VQV. So these many newtons of force. Now, how do you determine the direction of this force? Again, you can use your left hand rule. B is pointed into the plane of the page. Current would be the direction of flow of positive charges. So if this was a negative charge, for example, you would reverse the direction, okay? Because current is always the flow of positive charges, or opposite to the flow of negative charges. So in this case, current is towards the right. So my force then is towards the upward direction. So there will be a force applied on this charge towards the upward direction, which would make this charge in the next instant, let's say the charge is here now because it has been deflected upwards, okay, and the velocity then will be in this direction. Okay, now when the velocity has moved direction, you will see with your Fleming's left hand rule, the force will also remain perpendicular to the direction of the velocity. Okay, now since the force is also changing direction and it's always perpendicular to the velocity of the charge, this charge will assume a circular path. Okay, so the charge will assume a circular path. Now we know that whenever an object moves in a circular path, the force applied on it will be the centripetal force. So the only force being applied on this charge here is F equals BQV. Okay, we'll ignore the sine theta as we are considering that this is moving at right angles to the B field. So this component of force BQV is actually the centripetal force, which we know is given by mv square over r, where r is the radius of the circular path. So this implies that BQV equals mv square over r. Okay. Again, we can also determine the radius that this charge is going to assume by solving this as r equals mv over bq. So if we know the mass of this charge, we know the velocity with which it has entered the B field, the strength of the B field and the charge itself, we should be able to determine the radius of its motion. Okay, 6.3.6 is simply solving a few examples using these concepts. So just doing these examples should strengthen their concepts a bit more, but I would advise that going through a few exam questions should also help. And remember, this is the SL portion, then the HL portion would cover these topics in more detail. That will be chapter 9. So yeah, that ends fields and forces.